Hello and welcome to GoSimulation.com, the only place online where you can find comprehensive SolidWorks simulation training. My name is Nick Leister, and in this video we're going to continue on simulating this bridge. Now in this series of videos we're going to focus on the approach called the crawl, walk, run approach. And in this crawl, walk, run approach, the idea is that we start out with a very simple simulation, and then we gradually make the simulation more and more complex until we get to our final simulation. In this video, we're going to focus on the walk section of the crawl, walk, run system. Now, in this video, what we're going to do is make the joints of these beams a little bit more realistic. From the previous video, the joints were sort of out of whack, but we're going to fix that here in this simulation. We're also going to apply the correct force to the correct location on this model. Finally, we're going to apply the correct materials to the different components within this simulation. Now, let's go ahead and get started. In our previous video, we had created the crawl simulation. But as you can see, in this crawl simulation, some of these joints are not behaving as we expect. Now what I mean by that is, here in particular, we have two beams which are meeting at this location. And at this location we should have one joint which holds these two beams in place. Now one of the problems with the crawl simulation which we had created earlier was that this joint had not only connected these two beams, but it also connected some of the other beams which were nearby. This can lead to a stiffer joint region than is accurate. And so what we're going to do in our walk simulation is we're going to fix these joints up a little bit. Now before we get started in doing that, what I'm going to do is just copy this crawl simulation to form our walk simulation. I'm going to right click and then select duplicate. And now I'm going to call this walk. And then click OK. Now that I've duplicated this walk simulation, the first thing that I'm going to do is investigate my joints. Now as you can see, I'm showing some of the simulation results on the screen, and it makes it a little bit hard to see because these joint bubbles are just pretty big compared to the rest of the model. So I'm going to clean that up by using my eyeglasses up here and then selecting my simulation symbols. That's going to hide the joint groups. And now when I edit the joint groups over here on the left hand side, the joints will pop up as needed. Now one of the questions that a lot of people have when working with SolidWorks Simulation is, how do I edit these joint groups to be the way that I want them to? Well, in the previous video what we had done was we had made the global joint group size 0.2 meters. Now what that had done was that had found all of the joints within our model, and then we essentially made those joints 0.2 meters in diameter. And then if two joints overlapped one another, those two joints would be merged into one joint. And that's how we have essentially created all of these joints to connect some of these components together. Now the problem with this is that when we're going through with this operation, a lot of joints get created where we don't want them to be. Some of these joints are connecting components which should not be connected. For example, this joint right here connects or should connect this component and this component. But if I right click on the joint, this will bring up my select joint members dialog window, and I can actually see that there are three beams which are attached to this joint. Now what that means for us is that when I mesh, what's going to happen is that because this software thinks that, I'm just going to click OK to this warning. When this happens, what the software is thinking is that this beam and this beam and this beam are all connected at that same joint, and this makes the joint much stiffer than it really is. So this is what happens. This joint not only connects this component to this component, it also connects all of these components to this component as well. And you can see that with this black section right here, this guy, which connects these components together. We don't want this joint. That joint isn't real. And so what we have to do is we actually have to go into the joint groups and edit them manually. So I'm going to do that again. I'm just going to come in here. I'm going to right click on this joint group. And the way that we do this is just by selecting the components that we either want or don't want within this section. So right now I've unselected this component from this joint group. If I make a mistake, and I can always just reselect it, right? But we don't want that guy. And now what I'm going to do is just go around the whole model and follow this same process until I get all of the joints correct. Now this is going to take some time, and while this is happening I just want to show you how the workflow goes. Right, so now I've pretty much edited 2 of these joints. I'm just going to click the calculate button again. That's going to recalculate. I may get these end joints right here. This is actually okay in our particular case. Now I'm going to click the OK button. I should get this warning message saying that the joints were recalculated. And now what I'm going to do is just recreate the mesh. Now I have been noticing a small bug where if I mesh, it shows that the mesh did not complete. Now the reason for this is unclear to me. I don't know what SPR that belongs to, if it even does belong to an SPR. But the way that I get around that is just by essentially clicking the run button, which should mesh anyways, and then that's when I'm going to get this error message, which I don't get if I just click mesh. I'll click OK to this, and now what I'm going to do is just come back into the joint group, recalculate. For some reason this is the process that I have to follow, and now if I click run, it should remesh. And then once the solver starts up, I'm going to click cancel. So this could take just a moment here. All I want to do, oh, that went pretty quick. All I want to do is show you what this mesh actually looks like. So I'm just going to jump into the mesh, show the mesh. And now that I've cleaned up this joint group, we don't have this crisscross which was happening before. You'll notice that because I have not edited this joint group, I'm still getting this connection which should not be there, but I need to edit this next. So if you look at the entire model, you'll notice that there are a lot of these sections. All of these joint groups are what we're going to fix up now. And while you're going through, I suggest that you remesh and just look at your mesh just to see the work that you've done in between. So what I'm going to do is I'm going to go through this process. I'm going to pause the video and I'm just going to see you on the other side, because this will take quite a while to complete. Now that we've cleaned up the joints a little bit, the model looks a lot better. Now again, the reason why we were doing that was because these connections between some of these beams, those connections are entirely rigid. That means that they don't flex at all. And this, remember, makes the model much stiffer than it actually is. So the next step that we're going to do is apply materials to some of these components. Now, the majority of these components are made out of pine. Now, as you may or may not know, pine is what they call an orthotropic material. Orthotropic simply means that there are different material properties in different directions. Now, the reason why that is because of the grain structure of the wood. Now, because we're only in the walk simulation, we're just going to keep things very simple and apply an isotropic version of pine to some of these pine components. Now, in addition to the pine material that we're going to apply, there is this sleeve that runs on the outer portion of this component. What I'm going to do is just hide the mesh so you can see this. This outer sleeve right here, this is actually going to be made out of PVC. And so we're going to apply the material properties of PVC to that. And then this inner component, this is going to be made out of plain carbon steel. So let's go ahead and begin. The next thing that I'm going to do is create the pine material that I'm going to apply to most of these beams. Now the way that I'm going to do that is by entering into the material database. Now to do that, I just right click on parts right here and click Apply Material to All. And now what I'm going to do is just browse out into my Woods folder, and what I'm going to do is make a copy of this pine material. Now the reason why I don't just use this pine material is because this default pine material doesn't have a lot of the material properties that I'm going to need. And so I need these material properties, and I cannot edit these material properties in the default database. So in order to get around this, I'm just going to right click, copy, and then I'm going to make another folder here for wood. So I'm going to right click, new category, I'll call this wood. And now what I'm going to do is just paste, or right click and then paste my pine material into this folder. And now what I'm going to do is just enter in the material properties which I had listed before. Now if you're confused about why I'm entering the material properties like I'm entering them in here, I describe it very well in lessons 5 and 6 of the course that I actually sell on this website. So if you're curious about that, just go ahead and check it out there. Now what I'm going to do is just enter in 12,000 for the elastic modulus. For the Poisson's ratio, it's going to be 0.3. The mass density, we're going to change that to 600 kilograms per meter cubed. And then for the yield strength, I'm going to change that to 103. Now again, the wood doesn't really have a yield strength, rather. It has a fracture point at which it breaks. So it doesn't exactly yield, it's a brittle material, and so it breaks. But what I'm doing here is just entering in the yield strength because I'm going to use the von Mises stress as the failure criterion for this wood. And again, the reason why I'm doing that, I describe it very well in lessons 5 and 6 of the course. So now what I'm going to do is just click Save and then Close. And now what I'm going to do is actually apply that wood to all of these components. Now I actually know that a lot of these other components, such as this outer sleeve and this inner sleeve, are going to be made out of different materials, but we'll do that later. We'll handle that in just a second. So what I'm going to do is just right click, Apply Material to All, and then browse out to that material that I had just created, and then select Apply, and then Close. And now what I should notice is that all of these say pine. Now the next thing that I'm going to want to do is apply the correct material to some of these other components. Now once I click on this inner sleeve, what will happen is it will show me what component I've just selected in the tree on the left hand side. And so all of these inner sleeves, these guys, I'm going to apply plain carbon steel to these inner sleeves. Now what I'm going to want to do is just hold down the Shift button and then select all of these components, right click, and then apply Edit Material. And now what I'm going to do is just browse out into my steels, steel, and then I'm going to select my plain carbon steel, select Apply, and then Close. And now for these outer sleeves, those are towards the bottom here, and they're all indicated that they're PVC sleeves by the name right here. So all of these guys, I'm going to Shift select them. I'm going to apply a PVC material to those components. So that is located under Plastics. And what you'll notice is that we actually have two PVC materials. We have this PVC rigid and this PVC plasticized. Now what you'll notice is that neither one of these two components has a yield strength associated with it, but that's okay. We actually don't need to apply a yield strength to this if we're not actually calculating, or we don't care about the stresses within these sleeves. And so what I'm going to do is just select this PVC rigid and then select Apply and then Close. The last thing that I'm going to do is apply a force of 62.5 pounds at each one of these joints downward, or in the positive z direction per this global coordinate system. Now this is a little bit more realistic to the total weight that we're going to apply to this structure. So in order to do this, I'm just going to go ahead and right click on this force which we've already created and then select delete. I'm going to click yes to this, and I'm just going to create a new force. Now I'm going to apply this force to joints, so I'm going to select joint right here. And I'm just going to make sure to select this middle joint right here and then this other middle joint on the other side. And now for my direction, the direction is going to be straight down. So there are a lot of faces that are normal to this direction. I'm just going to zoom in on one of them and select that. And now what I'm going to do is select this normal to plane option because the force is going to be normal to that plane, and I'm going to enter in 62.5. Now what you'll notice when you're working with these joints is that there's not an option to select per item or total. By default it's just going to be per item, and so what I mean by that is there's going to be 62.5 pounds of force on this joint and 62.5 pounds of force on this joint. And now what I'm going to do is just zoom out and make sure that my arrows are pointed in the right direction, which they are. And now I'll just click the OK button. And so that's it. The next thing that I'm going to do is just run this and see if I get some results. And now that I have some results, the first thing that I'm going to do is just jump straight into my deformed results here. The reason why I'm doing this is just to see if the results that I see on the screen, these exaggerated results, are behaving in a manner which is similar to what I was expecting. Now what I like to do when I view my deformed results is just right click and then animate, and this gives me a very clear indication of what's actually happening within the model. So it looks like these results are okay. I'm just going to go ahead and click the cancel button. And now I'm going to exit out of the deformed results. Now one thing to note is that when we're viewing the stress, we have to be very careful. And that's because we're working with multiple material types. Now we have a wood, we have a PVC plastic, and we have a steel. The wood is being treated as an isotropic material, and the PVC plastic is being treated as a linear material. Now we see all of the stresses on the screen right now all at the same time, and all of these different materials have different failure criterions that are associated with them. And so we have to be careful because a high point in the stress isn't necessarily a dangerous point within the model. It just depends on the way that we look at stress and the yield stress of that particular component. And so a better graph, instead of the actual stress graph, is actually just to look at the factor of safety. So I'm going to create a factor of safety plot, and that factor of safety is going to compare the yield strength to the actual stress seen in the model. And now remember, those PVC components, those components do not have a yield strength, so we're not considering the failure in those components. What I'm going to do is just have this automatic option selected and then click next. Remember, what this will do is this will take with it the failure criterion that's associated with the model or the material. So I'm just going to click next, next, and then I'll click the OK button. And I get this warning message because as it says, some of the materials don't have the yield criterion. This is for those PVC components. Just click OK to this. And now we can see what the factor of safety throughout the model is. As you can see, the smallest factor of safety is about 61. So we're dealing with a pretty safe model. Now what I'm going to do is just right click on the factor of safety, and I'm going to show where the lowest factor of safety is. So in order to do that, I just right click, click Settings. Actually, it's under, pardon me, it's under Chart Options. I always get these confused. And now what I'm going to do is I'm going to show the minimum annotation here. This is showing where the smallest factor of safety is, and now I'll click the OK button. So this is indicating that the smallest factor of safety is located around here, towards the center of the part. And so what this is telling me is that in the run simulation or in subsequent simulations, what I'm going to do is actually focus on this region of the bridge. And what I'm going to do is essentially not model the rest of the bridge. I'm just going to model this section, and then I'm going to use solid components, and I'm going to get a much clearer indication of what's actually happening in the model. So this pretty much concludes the walk section of the crawl, walk, run videos. If you have any questions, please ask them in the comments section below. And again, please make sure to sign up for our email newsletter so you can stay up to date on all of these videos. Thank you, and welcome to GoSimulation.